All right, how's it going? Welcome to the official course overview video in this series here on vector calculus. If you're a returning member to the channel, welcome back. It's good to see you again after a short break. But if you're new to the channel, I just want to quickly describe what this video is, in case we're wondering. So at the beginning of every new video series that gets posted on this channel, I'm going to make what's called a course overview video, where we are trying to accomplish two main goals in this video. The first is just to give you a little bit of an outline as to what to expect in these videos, so you're not wondering, and then you start watching several videos down the line and you're saying, okay, this wasn't what I was hoping for. So you get an idea of what to expect. And then also we want to go over just some prerequisites. So in case you're wondering, do I have the mathematics or physics knowledge needed to understand some of the concepts in this video? Well, we're going to give you an idea of what you can expect in terms of that. Okay. So let's get into it. First thing, in terms of prerequisites, there are two primary prerequisites. The first and the biggest one, in my opinion, is linear algebra. For those of us who are familiar with linear algebra, hopefully that kind of makes sense, right? One of the most common objects that you would see in a linear algebra course are vectors, right? You also see matrices as well, but vectors are an integral component of linear algebra. And if we are doing vector calculus, the calculus of vectors and vector-related quantities, you can imagine that it would be essential, right? So we definitely want to make sure that we have a good understanding of linear algebra. So I would say that's probably the main one, but there's also differential equations that we're going to see show up throughout the video series, particularly more towards the end of the video series, where we're going to see that certain vector operators are naturally going to lead to differential equations which have to get solved. And there are multiple problems on the problem sets that involve solving differential equations after applying a vector operator. Okay. So these are the two main ones that we're gonna want to make sure that we have before starting the video series. Now, that being said, let's get into the actual content, right? Which kind of the fun stuff. So this is kind of split up almost. It's split up into several different subsections, but if I had to personally split this up, I would almost describe it as these first three sections have an overall goal. Then this middle section right here is almost like a little intermission. It'll be a very short section on just a single video. Then these next three sections right here describe an overall goal. It'll act as kind of a transition period in the video series. And then finally, there's this very interesting section at the end here that will be its own set of concepts. Okay. So the first three kind of all revolve around the idea of trying to generalize some of the ideas that we've learned in single variable calculus, saying how can we generalize this to vector quantities and in higher dimensions, and how do we do calculus in those dimensions? Okay. So starting with this first section right here on derivatives and coordinates, we're going to be looking at different types of functions that are going to show up throughout the video series. So this is going to look at scalar functions, vector fields, and stuff like that. And then we're also going to be looking at what does it mean to differentiate those quantities? How does the derivative generalize from what we normally think of as the derivative in just one dimension? Okay. So we're going to look at that, and then we're also going to look at a couple of coordinate systems besides just the standard Cartesian coordinate system that we're already familiar with. Okay. Then, moving on to this next section here, we're going to be talking about curves and lines. And in this section, our first goal is to mathematically model what a curve is, be able to say that a curve is mathematically represented by this. And then what we're going to see is that at this point, we're going to start to move away from differentiation and we're going to start looking at integration. We're going to start wanting to integrate things. And now that we're working in a larger number of dimensions than the single variable calculus course, naturally we are going to want to integrate along a specific type of curve. And there's a name for that type of integration, and it's called performing a line integral. So this section is kind of building up and then talking about what a line integral is ultimately. So then moving on to this next section here on surfaces and surface integrals, we're going to see in this section how to integrate along a line or along a specific curve. It's here where we start saying, well, we can integrate along lines, but we can also integrate along surfaces or even volumes, right? So we're going to start to look at how we can integrate over more than just one variable in this sense. And we'll start off relatively easy and conceptual. We're going to start off in R2 and R3, but then we'll quickly generalize to Rn and we'll get into all the intricate details and interesting details that come with surface and volume integrals. Okay. And then again, that would kind of wrap up learning how to just do calculus in a higher number of dimensions, if up until this point all we've taken is single variable calculus. Okay. So that covers the first three sections. Then we're going to be looking at a quick little section on geometry, which is just talking about a couple of geometrical concepts related to everything we've been talking about in these first three sections. So now we'll talk about ideas such as the binormal vector, torsion, curvature, stuff like that, as well as a couple of interesting theorems that we're just going to briefly introduce. So that way, if you ever end up taking a course on geometry that's beyond the high school geometry, you could say, oh yeah, I've heard of those at some point in that one video, right? And this will be a pretty short section. Then it's at this point where we're going to move on, and in this next section on div, grad, and curl is short for the divergence, gradient, and curl. Those are the three really big vector operators that we see in a course on vector calculus. So what we're going to be doing is we're going to try to understand what they are. And when I say understand what they are, I mean not just how to calculate them. In other words, not just how to write out the mathematical symbols and perform the operations, but I want to give us a good conceptual understanding as to what each of these quantities are. Okay. And also, just in case we're wondering, it is going to be at this point when I explain the meaning behind the channel name divergence is divergence. It is not just a random name I completely came up with. There is a story behind it. So it's at this point where we will explain the reasoning or the story behind the channel name. Okay. Then once we have a good conceptual understanding of what the gradient, divergence, and curl are as these operators, we're going to apply those operators in various integral theorems. So we're going to be looking at theorems called the divergence theorem, Stokes' theorem, Green's identities. I think we'll look at the continuity equation in there as well. So we'll be looking at these interesting results, and the goal on my end is that I can explain the divergence, gradient, and curl in such a way that the integral theorems almost just naturally lay themselves out. I don't want to say that they're trivially true, because it's kind of almost minimizing just the beauty and interestingness of these theorems, but I hopefully want to show that these theorems do not need to be these intimidating things that they were to me when I first took vector calculus or courses involving vector calculus. Okay. So that's what we're going to cover there. Then moving on to physical applications. Vector calculus is inherently an applied math, or I should say it's an applied, what am I trying to say? On the spectrum of pure math and applied math, it falls more within the realm of applied math. And it has a lot of applications to physics. It gets used all the time in electromagnetism, fluid mechanics, and even in other areas as well. Almost every upper division physics course will involve vector calculus in some way, shape, or form, if not all the time. So we're going to be going over different ways where this shows up in physics. We're going to be looking at Gauss's law for both a gravitational field and an electric field. We're going to be looking at, let's see, what else? We're going to be looking at Maxwell's equations. I'm sure there are probably a couple others that, we're going to be looking at the Laplace's equation, Poisson's equation, and then the continuity equation, if I haven't already mentioned that. And we're going to see how what we've been learning so far applies to physics. Okay. And then finally, We're saving the best for last. We have a section on tensors, and it's going to be a decent sized section. I can personally say that the specific question of what is a tensor absolutely plagued me during undergrad. It was something that I felt like everywhere I looked, I was getting a different definition, and even though I felt like I was gaining knowledge into what a tensor was, I was almost getting more confused at the same time. So our goal is at the very beginning of the section to give a clear answer as to what is a tensor. We're going to learn about how to operate on tensors, some basic tensor operations, how to decompose tensors. We'll see that for certain types of problems that is useful. And then we'll finish off with a couple integral theorems relating to tensors. Okay? So, a very fun one that I'm personally looking forward to at the end. So, hopefully this sounds interesting. Personally, I don't know if you can tell, I'm excited to be making a video series here on vector calculus. So, yeah, hope you continue to watch, and that I'll see you guys in the next video.